let's get started. Welcome to today's session. And I think this is our second last session, right? So Andrew will continue the topic of fault tolerance today. So the session here, Andrew will cover basically based on the paper by Daniel Gottsman, the fault tolerant quantum computation with constant overhead here. So let's welcome Andrew to begin his talk here. Yeah.
Thanks. So I'm just going to talk about a different fault-tolerant computation scheme compared to what Kishore talked about last time. Um, so just do it this way. There we go. I'm going to talk about this scheme proposed by Dan Gottsman in back in 2014. So I just have this simple figure. Hold on, let me just grab my virtual pencil. So last time Kishore talked about a concatenated code scheme for fault-tolerant computation. So that's kind of like you you have some physical qubits and some set of them, like you encode it to some correcting code, and it constitute like one logical qubit. And then okay, now you got four logical qubits, and those four logical qubits serve as the physical qubit in this larger code, encoding another like second level logical qubits, and then you take a bunch of them, and then like you do stuff on them. um but you can do a different um scheme by kind of like just taking bunch of different quantum error correcting codes that encodes multiple logical qubits. So in this figure, I can have this one quantum error correcting codes, which has, I don't know, what is this, like 16 physical qubits, but they encode three logical qubits. So in this scheme, I can also encode, do this computation on 1, 2, 3, 4, 5, 12 encoded qubits, but now I kind of like partition them into different codes, right? So every three logical qubits, I encode them in this one QEC code that encodes three logical qubits, and I just do like encode them on um four 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 copies of the same code, right? So I get 12 logical qubits. So that's basically what kind of like underlies this Gotsman constant space overhead fault-tolerant quantum computation scheme. So, okay, so if I have a circuit C with k qubits and fk locations, I'm going to talk about what location means. Then I can simulate this fault-tolerantly using order of k logical qubits and polynomial of k in terms of k locations. So location is basically just kind of like an abstracted unit of circuit. So it's kind of like where um, a potential fault in the circuit um, could come from. And as so that's described by this figure. So you could have some preparation location where I want to prepare some ancillas, and I have locations where I do some gates. You can have this logical 2-qubit logical gate location and 1-qubit logical gate location. And then I can have some space, some locations where I just do nothing, right? So that qubit just waiting for the next thing that I'm going to do to it in the circuit. And I also have some locations correspond to measurements. So but that's basically gonna it's going to be kind of like the lowest level building blocks of the circuits that we're gonna talk about in this scheme. So there are basically kind of like six points or like components that comes that like basically are the ingredients to make this fault tolerance scheme. So the first one is, like I just mentioned. So now I block encode. So if I have k logical qubits and I divide them over m copies of this RC QLDPC code. So I'm gonna explain what that is later. And I want that code to have some, like um, non-zero asymptotic encoding rate. Um, and then in this scheme, we only do one logical gate at a time. So in this kind of like abstracted, or encoded circuit layer, I only do one logical gate, and then another logical gate, and so on. Oops. And the third component is this like cycle error correction. So I kind of like do error correction across like this M blocks. I'm gonna explain what that means more precisely later. Um, and then the error correction scheme or like syndrome extraction that we're gonna use is the Shor style syndrome extraction. I'm gonna explain that later as well. Um, and then to implement logical gates and logical measurements, we use this nil style teleportation. Yeah, with some offline ancilla preparation that you need to do this teleportation. And yeah, like last thing, like we want to kind of like ensure, that we have this local stochastic noise below some threshold, which I'm going to guarantee that we can, have this constant overhead, space overhead and polynomial time overhead. I'm going to talk about what local stochastic noise means later. Yeah, so this is like the outline for today. Not gonna go through everything. So I've decided to go a bit slow and into a bit more detail about how you go about proving this threshold theorem. So today, yeah, I just did that. I just did description and ingredients. And I'm gonna talk about in a well, somewhat detailed explanation about what what QLDPC code we want to use and what is the QEC protocol. And then I'm gonna talk about the threshold theorems and the assumptions that go into it. And then I'm gonna go through like probably like the one third, the first third of the proof on bounding error rates for the QEC cycles. And then the rest I'm gonna talk about next week, and those will be what the logical gates and measurements how they're implemented and how they go about go into the rest of the proof and then do the space and time overhead analysis. That's next week. Yeah, in this first bit, we're not going to talk about like the error rates and all that stuff from logical gates and measurements. Right. So first, quantum LDPC code. Right. So basically, I'm just probably just repeating this from a few lectures back from Kishore. A QLDPC code family QI. So I have like this like infinite family like Q0, Q1, Q2, and so on. And these are basically either CSS code or just a general stabilizer codes that are not necessarily CSS. And it has these parameters, and it has sparse parity check matrix, which is defined by this R and C parameter. And this means that so this each stabilizer generator. So those are the stabilizers that I'm gonna measure to determine if there's any error, and it acts on at most R qubits. So the stabilizer weight is at most R. Um, and each qubit in this code, like this, each of this Ni qubits, they only participate in at most C stabilizer generators. And this R and C are constant independent of NKD. Um, so we want this rate to be non-zero. So say if this Ki is a constant, that I'm not gonna get that. So the toric code is um it's not one of the code families that we want to consider here, or like the surface code. Um and we want this distance to go to infinity. Uh so we could impose this requirement that it um grow as like as square root of ni to get a good threshold. And we also impose like this additional condition on how the number of physical qubit or data qubits grow. And it has to be, the difference between like the next code in the family and the current one is, has to satisfy this, which basically means, like it kind of like it has to grow. Um, and the last thing is that requirement of the QLDPC code family that we want to use here is that we want a um, we want some decoder to exist such that the logical error rate is bounded by this inverse function, this polynomial function. Um, yeah, so that we can kind of like later on you'll see that we need this to guarantee like the error rate doesn't blow up. Um, yeah, and we're gonna do like this error correction across like this um multiple copies of these QLDPC code. So one code that is pretty well known that satisfy these is the hypergraph product code, which kind of like described in this figure. If you take like these dark gray squares as physical qubits, and the white squares as the checks, then like this blue ones are qubits in the support of this blue check, and this red ones are in the support of this red check, or like Z and X checks. Um, yeah. So that's kind of like what the requirement that we want the code to have. Talking a little bit about, I'm going to talk a bit about the error model. This is so local stochastic noise, which means is that, okay, so if I have like as a set of locations in my syndrome extraction circuit, then the probability that I have error, like all of these the components in this set as are faulty is bounded by this probability p raised by the power of how many components I have, how many locations I have in the set S. And yeah, so for decoding, we want our decoder to have like this property that I've shown you before, like this bound on the logical error rate, um, to be satisfied whenever some threshold, well, multiple thresholds are satisfied. And I'm gonna explain that in the next slide. Um, and yeah, whenever we have that, then the residual errors is going to be local stochastic with this rate, right? This P0 rate. So that's going to replace that uh, this p here later on. You'll see. Um, yeah. So to do that, so there's this theorem that we need later on to show the threshold. And this is that we want this quantum LDPC code to satisfy this four conditions. So if I have this initial error rate, this p tilde, so if so that will be the rate of error on the incoming qubits on every QEC round is to be below this threshold p0, and I want the error rate per physical qubit in each syndrome extraction cycle to be below this threshold P1, and this syndrome bit flip error rate to be Q to be bounded by this P2, right? So in every like syndrome extraction cycle, I measured multiple stabilizers, and I can there could be like errors that in my measurement device that can flip the measurement outcome, or it could be there could be like some data errors in the actual qubits themselves, and there'll be like the speedy there'll be like the errors inside the syndrome extraction cycle. Yeah, and we want this to do like to repeat the syndrome extraction cycle di many times. So di here is the distance of the code. So if the code satisfy all these four conditions, then the logical error rate must satisfy this. Yeah, this is a bit lengthy um, expression, but what this basically means is that the error rate is suppressed exponentially um, in terms of the distance, right? So if I increase the
So so
distance,
so then you want like a smaller blocks, right? For maybe, I mean, because it also depends on NI, right?
yeah, but it's only like a linear, like it's gonna be
No, no,
like
but yeah, okay. So this di by 4 that will suppress, because the term, like in the bracket that's between 0 and 1. So as you increase distance, that will go down. So you
yep,
benefit
yep,
there.
right.
This NI will cost you. So maybe, I mean, I'm wondering, is this the reason that sometimes people, for example, there was a recent also a paper where they tried to take the uh, Gottman's proof for non-stochastic, or I think a stochastic to non-stochastic setup, and they tried to divide like the code into different blocks, and then you treat each of the blocks separately. So if you have a smaller blocks, then your NI is small. And if the NI is small, then like maybe your logical error will be small. Because
Um,
it's a multiplicative factor, that's good. Anyway, you have a O there, like, I mean, so
yeah.
some constant does not matter. But still I'm wondering, like if we bring down NI to a constant, maybe that will be a good thing, right?
Yeah, but if Ni is just a constant, then like you're gonna be bounded by some bounds, right? Like I don't know, like some Hamming
No,
bound or something.
so I'm thinking,
Like
Andrew,
the
like let's
distance.
okay. I was thinking like
Like
a big code, and then you break it down
like
into. Yeah, I understand. Like to have a big D, you need a big N, and
exactly.
yeah, and yeah. So somehow
So
the amount of
so
separation that you want, you pay the cost in terms of N. But the good thing is that the separation is exponential. So
right.
like, I mean, and the cost is linear. So maybe it's okay. But yeah, I mean, yeah, okay.
Yeah, yeah. Yeah, exactly. I don't know, probably like yeah, I don't know what's best because like I mean if you have like a good QLDPC code, then D and N are are both um
No, no, I mean
yeah, D's of
they
n.
will be of the same order, right? I mean,
Yeah,
so D will be
yeah,
constant times n, right? Yeah. So yeah.
right. Yeah, and that's probably like the best that you can do. I'm not sure. Hmm.
Yeah, like I mean, this I'm not liking the n there. If this expression could be n independent, that would be very nice. But yeah, I mean,
Ah,
like I
yeah.
mean, like is
But in,
n really needed there, or is it like because of the scheme that we are using?
but the
Mm.
n hardly makes a difference to the overall scaling, right? Considering it's like in an exponential, you
Yeah, yeah,
just
correct, correct,
multiply.
correct.
Yeah.
But I'm thinking about, let's say we are working with millions of qubits.
Yeah. Yeah, even if D is like order of square root n, then you could it's probably fine. I'm not sure.
Yeah, yeah, no, no. I mean, anyway,
Yeah.
like here we have a O, right? So anyway, there are some constant that lurking
Oh
there.
yeah.
But yeah, I was thinking it would be nice to, like have I mean, as a, let's say, even if we don't think about practicality, like, just as a curiosity question, that do we really need NI there? Or I
Yeah.
mean, or NI is just an artifact of this particular scheme and that appears in the theorem.
Um
So where does this ni appear from? Maybe that gives us a better understanding.
yeah, yeah, I need to yeah, I'm not going to go through this theorem for proof, but yeah, I need to go back and look into the proof of this in more detail. I'm not 100% sure. Um Yeah, but I mean, like, I guess like intuitively, like, as you have more physical qubits, then you have more locations where error could occur. So that kind of like has to be somehow goes into the logical error rate. Um, that would be my best guess. Because you see, right, like this is has like this PD there. So yeah. Yeah, but anyway, like so basically like the reason why we need this theorem is that so we want this guarantee on the logical error rate and the residual error rate whenever our code satisfy um these conditions. Um which gonna be useful later on. All right, so now I'm gonna go through the error correction protocol. Right, so yeah, so in our error correction protocol, we're gonna measure the syndrome repeatedly to ensure, like to kind of like get rid of the artifact of this erroneous syndrome measurements. And so what we're gonna do is that we're gonna split, we have this M blocks that I showed you earlier, and we're gonna like partition those further into S sets, and then we're gonna measure syndromes in the set one, and then the rest of them we gonna do nothing, and then measure set two, and then the rest of them we're gonna do nothing, and so on. Um, and yeah, so the reason why we want to do that is that because we need to have we need to use some ancilla qubits to do this syndrome measurement. So to get this kind of like constant space overhead, we want to reuse those ancillas to measure like different blocks. So that's the reason why we want to split those blocks further. Um, and the error correction scheme that we're going to use here is the Shor style QEC scheme. Um, so okay, so if I if we have this we use this RC QLDPC code. So the weight of each generator that we're going to measure is going to be at most R. Um, and so what we need to do here in this sure style error correction is that first we want to prepare this cat state, right? So it's defined like that, and W is the weight of the generator that I want to measure. And then I want to apply this controlled Pauli gates. Oops. And then I measure each ancilla in the X basis. So it's explained in more detail in Daniel Gottsman textbook in this two subsections. And so this is basically just a simple illustration. So if I want to measure this weight to Z check, then I just need to prepare this maximally entangled state on this two ancilla qubits, and then I do this controlled Z gates, and then I apply Hadamard and do computational basis measurement, and then I take the parity of those two measurements, and then I get the syndrome of this weight to Z check.
So basically, if I want, let's say, yeah, so if I want, let's say, cat state, which has, let's say, D qubits, or let's say W qubits, then the circuit depth will be W.
Not quite, because you can do like this controlled Z qubits simultaneously, right? Because these two are on disjoint qubits, right?
No, so I'm thinking, so let's say depth, like 0, 0, 0 plus 1, 1, 1. Like I'm thinking, what will be the depth of such a syndrome circuit, measurement circuit? Like, because that is also one of the things that people want, is that syndrome measurement circuit, it should be small depth.
Oh yeah, sure.
And I'm wondering the motivation for preparing the cat state, whose weight is, I mean, like I'm saying that, because I'm thinking that, like, because they are, I mean, I'm anticipating, I mean, I might be incorrect, but I'm anticipating. So let's say we are talking about, like these LDPC codes who have constant weight. And that constant weight, let's say if that goes into the cat state number of qubit, and so that will imply, like a constant depth syndrome measurement circuit. So that's a good thing to have.
Yeah. And you will also have some, like it's not just this, right? You still need to prepare this. And that's in the next slide.
Yeah. So you need to prepare the cat state also. To prepare
Exactly.
one, yeah, but it's okay, right? I mean, W is a constant for a constant, like LDPC code.
Yeah.
So for a constant W, any function will be it will be a constant depth circuit, like for a fixed W. So you need to prepare a fixed cat state, and then you need this syndrome measurement circuit, which will be also again. Oh, but how does this circuit size like, I mean, so cat state can be prepared in constant depth. So that makes sense. But what about this? This is also okay, right?
This is just a single layer, right? No matter how, if W is 30, then this is still a single layer.
Yes. So basically we will have a constant weight, constant depth syndrome measurement circuit.
Yep. Pretty much.
Okay, very nice.
Yeah. So that's basically the next slide here. So how you want to go about preparing the cat state. And yeah, Kishore's absolutely right. So yeah, you just need kind of like constant, the depth of the preparation circuit of the cat state is basically just gonna be the weight of the stabilizer that you want to measure. So yeah. So okay, so what would one want to say here? Yeah, so this is the number of ancilla qubits that I'm going to use, right? At
But
most.
I don't know, maybe it does not matter, right? But I think using adaptive, sorry, I'm maybe asking you too much question. You asked toward the end. But using these intermediate measurements and feedback, we can further reduce the size of this. It's called poor man's cat state or something, right? And maybe we can say like those things where, like, I mean, you do not need. I mean, okay, I mean, it does not matter. It remains a constant because you have, like, constant number of qubits. So, but still, I'm saying one can cut. I mean, in this asymptotic analysis, does not matter much what constant we are using. But I think when people will start doing fine-grained analysis, one can save some cost here, and a lot of things that are going inside BGO, we can save some resources there. I mean, maybe in future one can do like here maybe they did not look at it. Yeah, but I mean,
Yeah.
yeah.
Yeah, I have to say, like in this, well, what I feel when I'm reading this scheme is that okay, so whatever works, to get this constant space overhead, like even you get like this polynomial time overhead, which is kind of like worse compared to like previous schemes, but yeah. Uh, Yeah, yeah, we need to prepare at most like this ni minus ki are ancilla qubits. So ni minus ki, this is basically the number of um stabilizer generators. Um and yeah, so this the number of cat state a number of ancilla qubits is just order of ni basically if k is order of ni and r is a constant. Um, yeah, so we want to prepare like just this cat state, uh, yeah, and measure the stabilizers, and so this is kind of like the circuit that I want to use when I want to prepare like this 4-qubit cat state. And then I want to kind of like add like this extra measurement to kind of like make sure that kind of like detect if anything goes wrong in this first circuit. And then if I see like something funky, and I'm just gonna throw that away and prepare a new one, right? So that's this third step. Um, so yeah, so the error rate for preparing this cat state plus like this error checking for any errors is basically going to be bounded by this, right? So P is the probability of any location, any faulty location. And A is the number of locations, total number of locations in the circuit. And I get like this 1 minus P in the denominator because I'm doing this post selection. Um, and yeah, so this is the syndrome extraction cycle. So yeah, if we can measure the generators that don't overlap with each other in parallel, and then yeah, like this WR for cat state. So that's basically what I just mentioned. Oh yeah, so this is basically the total number of ancillas that we want to use, right? So we have like this 4 qubits um, to for the ancilla cat state itself, and this extra 1 qubit to check for any errors. Um, yeah. Um, yeah. So yes, it's not particularly important, but like kind of like this is kind of like we want to choose how we want to partitions like all this M blocks, which is this S, to kind of like um make the come to the constant space overhead later on. Well, not later. I'm going to talk about that next week, but damn it. Let's go back. Yeah. Um, yeah, so measure across like this as sets of blocks, and the other one's gonna wait. So those that are the blocks that are waiting for for me to measure it, it going to accumulate this waiting noise. So we're gonna take that into account later on. Yeah, so those are total qubits and ancillas.
And also like Andrew, or like, I mean, do you care about these
Uh-huh.
things? Like, I mean, because we may want to have one shot error correction versus, like
Yeah.
like do we care? Like, do we need one shot here?
Oh, no, no, not for this. Um, so yeah, I think like there's like this extension on this, like that yeah, I can't remember exactly, but I think there's like a later scheme that improved on this that requires single shot. Then like you can do um you can get even less time overhead.
I see, I see. And also you're saying that you have different blocks. So you're saying you work with
Oh.
them and then other one waits. So is that the reason that gates are serialized?
Uh, so um not quite. So the serializing the gate is basically just, I do like one gate and then like some QEC cycle and I do another gate even though those two gates don't overlap and then I do QEC cycle. So I think this is just to make kind of like the analysis easier. But this separating into like this blocks, say like I have like this so this is two blocks and I have like two more blocks. Um so if I do like syndrome extraction on all this four simultaneously, then I'm gonna need ancilla for this, ancilla for this, ancilla for this, ancilla for this. But if I partition this two and I partition this two, then I only need this two ancillas to use to do syndrome extraction on this two and then reuse that for this other two. Um, yeah. So yeah. So now moving on to threshold.
So just to make sure I understand, you're saying
Uh-huh.
that serializing allows you to finish one syndrome extraction cycle and then sort of reset the ancilla so that you can use it in the next round.
Yeah.
And that's helping you keep the overhead within constant scaling.
Yes. Yeah, yeah.
Mhm.
Yeah. Um, yeah, so this is the scary looking threshold theorem. So if you see like the original paper, like the threshold theorem is like half a page long. And I'm just gonna go through each points in the theorem one by one. So yeah, I'm going to try to distill like all the important stuff here. So okay, so we want to start with this QLDPC. Basically, I kind of like covered this. So we want this um QLDPC code that satisfy like this conditions. Um, so yeah, non-zero asymptotic rate, and constant weight and qubit degrees, stabilizer and qubit degrees. Um, and also like this decoding guarantee under local stochastic noise. So yeah, like this initialization error, data qubit error, and bit flip error. And if all of them are below this thresholds, then I'm guaranteed that there is some decoder that give me which can give me a logical error bounded by this um, function, and the residual error is also going to be bounded, given that I repeat the syndrome extractions Tni times, and each of the syndrome extraction circuit has this step. Um, and then like we choose some number. Yeah, I'm not gonna go through this, but basically like this are like just some numbers that's going to work in the scheme. I'm going to talk more about this next week when we do like this overhead analysis. Um, and okay, so if we have this QLDPC code, then if this error rate P, so this is the local stochastic noise, so the probability of each location being faulty, that's P. And if that falls below some threshold PT, then there exists um, this kind of like k this KO such that if my circuit C with k qubits larger than this number, it's not super important, but basically if I just have this circuit C that uses k qubits, then I can construct this fault tolerant simulation, this C tilde that uses this number of physical qubits. Um, and with statistical distance of epsilon from this true circuit C. So that's just the distance between the output distributions from this two circuits. And C uses like this this very long thing physical locations and the classical depth for so this is for the decoding circuit. But let's just forget about this too. Um, but the important thing is that if this TNI, so this is the number of time I repeat my syndrome extraction, if that's polynomial, then this number of this locations is going to be polynomial in K. And if I have polynomial decoding, then the classical computation that I'm going to use is also going to be polynomial. Um, Yeah, so that's kind of like so I'm just gonna go through like the assumptions in more detail that goes into like into this threshold theorem. So so the first one is that we have this local stochastic error noise, right? Um and this is kind of like in the kind of like simplified model. So we associate this error rate p tilde um, at at the start of every syndrome extraction cycle, and inside the syndrome extraction.
So like Andrew, here comes the controversial question. Huh? So so recently there was some discussion on Cyrus, right? About somebody wants change this stochastic to non-stochastic. And then some person said that maybe that's not so non-trivial. And they used and the claim was that in the recent paper where the stochastic noise was changed to non-stochastic, they used diamond distance to do the analysis. But in this paper, does Daniel Gosman use a diamond distance, or is it like
No. So it's just like by locations. So the diamond distance, like like you take the distance between like a noisy component and the ideal one, right? So if I have a C naught and I have some channel that implements the noisy C naught and take the diamond distance, but yeah, they don't do that here. Yeah. Um. Yeah, that was like that was a nice paper though. I think like if what the paper I'm thinking is the same. Um, yeah. Um, yeah. So we have like this error rate per data qubit and syndrome bit rate, syndrome bit error rate. Yeah, and we want this depth of the classical circuit that does the decoding, and then we have this bunch of thresholds that guarantees this logical error rate and the residual errors. Yeah, so those are all the things that we want that require from our QLDPC code. Okay, so what you've seen in that previous slides, those are kind of like a simplified model, but the model that error model that we start with is this so-called basic model. And the basic model is where you have this probability p of any location um any faulty of oops of a faulty location. So if I have k faulty locations, the probability is bounded by that. But now we need to translate that into this simplified model where you have like this three different rates, kind of like abstracted error rates, right? So the basic model is that I have like this bunch of locations where error could occur. Now I need to translate that into this errors before I start the circuit, and this error on the data qubit after the circuit, and some bit flip on the classical bits from syndrome extraction. Well, yeah, I'm taking way more time than I expected. But yeah, I'll just go through like okay, probably I'm gonna leave out like some just gonna go the very like just a couple first steps of the proofs. Um yeah, so basically I explained all of this so I don't really need to repeat this, but the point here is that okay, so I partitioned to this um um M blocks, and yeah, we want to pick like an index I, like a large enough code in this code family, basically, for this to work. Um, and okay, so now comes the mapping from the this basic model and the to the simplified model. So yeah, so basically what we do here is that, okay, so first what we want to notice is that each qubit is involved in at most C syndrome measurements or checks. Um, and then, so we need to associate like this low level faults to this data qubit errors and bit flip errors, right? Um, so basically, you could so this QEC round will involve like bunch of syndrome extraction rounds. So SE1, SE2, um, and so on. And yeah, so basically by doing something clever uh, by mapping like all the faults so I have like this say SE C, right? So if I map the second half um of this kind of the faults in the second half of the syndrome extraction just to the as a residual error rate like this bit tilde for the next round. So that's gonna go there. Then I can kind of like um show that if I have a fault in this basic model, so if I have like any faults in this left-hand side circuit, then that's going to translate to at most C over 2 syndrome bit flip error, like this associated to this guy here, this Q, and some data qubit error depending on like what kind of location it involves in. Or which location it involves in, right? So if I have like some control gate error, then I'm going to associate that with some data qubit error. So I have a single data qubit error there, and some bit flip syndrome bit flip error there. And if I have something outside this, like like some physical error there, then I'm just gonna consider that as the error, initialization error for the next round. Um, sorry, so yeah, have a quite few more slides. I'm just gonna go like, okay, so this physical error rate analysis. So okay, so now what we want to do is to calculate this probability PP and PB, and this PP is corresponding to a data qubit error, so it's something like that, and PB is this guy's on the bit flip errors. Um, So we want to get this from, just probability P of this being faulty, this being faulty, this being faulty, this being faulty, and so on. So the first thing that we want to consider is that, okay, so what if I have some errors here in the ancilla preparation, right? So if this preparation circuit has A locations, and that's going to depends on R, um, and I have so for every qubit, I only have at most C ancillas. So the probability um, of me getting some data qubit error, which is like some error here from a propagation from this ancilla circuit is that, right? It's bounded by that, so it's kind of like an upper bound. So okay, so what if I have some errors there, right? So that's the second thing. So I'm gonna have like at most C controlled gates for every qubits, right? Because every qubit is only involved in at most C syndrome measurements. Um, so this is gonna be oops, so it's gonna be should be a C there, right? So C times the probability of each gate being faulty, which is P. And the last thing is the errors that I'm gonna accumulate from waiting for the next syndrome extraction cycle, right? So if this single circuit has L steps, and we have like this partitions as not as partitions, then we need to wait for SL time steps. So this will be like SL times P.
So,
Um,
so you wait here. If it, let's say it's not, if it's single shot, then you, I mean, that helps you here, right? For the single shot decoding case, maybe.
yes, right. Yeah, I think that's gonna be accounted for later, because now you only need to have like O1 um repetition of syndrome measurements
So,
instead
so,
of
so, so, so so,
B.
Andrew, I'm trying to, like, pass my head. And so the reason that, like this work said that good LDPC codes are nice because the particular theorem that you showed on one of the slides. So the one thing is that because of these cat states, which you need to, because of this syndrome extraction circuit and the way the, like the syndrome extraction circuit is designed, it depends on the weight of your code, right? And if
Yeah,
you are using LDPC code, so then it's constant weight. So then your syndrome extraction circuit is constant depth. So that helps. The second thing is the particular theorem that you had, which used all this scheme, which you are discussing so far, had this Ni and then this separation in terms of Di.
yeah,
Now, if Di also goes linearly in Ni, then you manage to suppress very nicely. And
yeah,
with all this, you are basically, I mean, you can achieve the, like a target uh, uh, over qubit overhead of constant
yeah,
for the target logical error.
yeah, pretty much, yeah.
Okay, I see.
Mhm. But yeah, like there's more like that I'm gonna cover next week, because now you need like this gate teleportations to implement like the logical gates and logical measurements, and you need to do like distillation and stuff.
Correct.
Yeah,
I would also love to understand, like how this space-time overhead thing is that people are talking about. I mean, obviously, like 1 hour, maybe not much time, but maybe
yeah,
separately or something, like, because that's the frontier, right? And what is the, like the, what do you call this, like the lower bound? Like, why are we not able to push below this polylog bound that we have? The
uh,
space-time, I mean, yeah.
oh, I think it's the best one is isn't the best one is kind of like just log from this paper.
Ayata?
Yeah, isn't that just log?
I mean, a polylog, right? I mean,
Oh, is it
overall
polylog?
multiple space and time, right? I mean, it's still polylog, right?
Oh no, I thought like there's like this constant overhead, this
So
constant space.
so you say constant space, but the time was polylog.
Oh, was it? Okay. Yeah, I thought it's just log, but yeah.
Yeah. So I mean, maybe, but I think it was a long time ago, right? From the same conference, I think we are talking about. But yeah, overall, yeah, I don't know if we can, if there is some kind of fundamental trade-off. Yeah.
Mm. Um, yeah, kind of running out of time, so I'm just gonna go through this slide and stop. Um, or yeah, probably like this 2 slides. Um, yeah, so this is basically like what we have, right? Like so from the gates here, we have like C times P, and this is SL times P, right? So these are from the weights, and this from like errors and the data qubits that are propagated from the ancilla preparation errors or faults. Um, so basically, the error for each data error rate on each physical data qubit is basically we just add all of them up, right? And we get this equation one. Um, and now we use the property of the Shor syndrome extraction circuit being fault tolerant, which means that if I have an A errors, I shouldn't use A because that could that's not one that doesn't mean A error. So A is like some positive number. um, so if I have A errors inside the circuit, then at the output, I'm gonna have A errors as well. And that means we have this local stochastic condition. So if I have A data errors like inside my syndrome extraction, and then um oh sorry. So if the probability of having A data errors at the output is going to be bounded by that, right? This PP is the probability of data errors inside the circuit. Um, and yeah, so this is just so this one took care of this data qubit error, right? Like this two guys. So now we want to look at this, right? So the error on this two on this syndrome bit flip errors are could basically come from cat state preparation. So we get like the same number, right, from post selection and from A locations inside the preparation circuit, which is this guy. And then we can also have like an actual measurement error. And if so, R is um, the upper bound on the weight of the stabilizer. So we have at most R measurements like this guy, and at most H Hadamard's, and at most R controlled Pauli's, right? So we need to take all of that into account, and then we get 3RP. And that's basically how we get this equation too. So yeah, I'm gonna stop here. And so for next time, I'm just gonna go through like so we still haven't talked about like because you also have like this initialization error, right? So that's what we're gonna start with next time, and then and putting things together, including like the gates and measurements and the overhead analysis next week. Thanks.
Any questions from the audience?
So actually, I want to ask about the decoding, right? Basically, if you assume that the decoding is polynomial n, right?
The
Decoding time, the time to decode, the classical time to decode is polynomial.
yeah.
So
Yeah, so
basically, I mean, wouldn't that mean that basically as you scale up, like you have to wait longer and longer for your decoder to finish, right? So this causes
yeah.
more and more idling errors, right? Isn't
Toby, there is nothing but time
So-
overhead here. So that's
Yeah,
what I was guessing what. You were talking about
So
space time overhead.
Hmm.
Yeah. Yeah, Andrew, yeah, please.
Yeah, so that's okay. So I think I forgot to mention one of those. I don't know if I even wrote that down, but that's one of his assumption here. So you can do like this polynomial time computation for every step of quantum computation or something like that, that kind of like bypass kind of like this decoding problem.
I mean, Hayata also, right? Here's something like you let the decoder run, and while the decoder is running, your quantum computation can also proceed. Like,
Ah, yeah, possibly. I can't remember, but yeah.
yeah, I mean, there is some, but like the worry is that, like, let's say if we want the space time, let's say if we care that, like the decoder run time, like in the classical decoder time is not free, like we have to take that into account.
Yeah.
Then the lower bound, the space-time lower bound will be bounded by the bottleneck can be the decoder runtime. And the thing is that here we are doing some kind of a rigorous analysis. Obviously, one can talk about, like, I mean, log time or linear time or whatever, like, I mean, in a non-rigorous setup, like, heuristically. But do we have decoder with guarantees that can run in constant? Like if you want the space-time overhead to be constant, the decoder has to also run in constant time. And that is somewhat, I don't know, like, I mean, is not clear to me, like how to take the decoder time into consideration if we want the space-time overhead to be constant.
Yeah. I'm not sure. I think that's yeah, I'm not even sure like how do you make like a good like a fair accounting for those like classical and
Yeah,
quantum
but
computation,
I
you know,
mean,
like
like noise will not wait, right? It will say, okay, there will be identity gate, you decode, I will wait. Like, I mean,
right.
like the environment won't be, like kind to you while you are decoding.
Right. No, but I mean like now do we need to like like design like a classical circuit with like AND gate and NOT gate to make like a fair accounting. I did, yeah.
Yeah, the question is that, let's say, even in the classical case, when people talk about space-time overhead, what is the best estimate they have? Like the LDPC code give them, maybe constant overhead, maybe, I mean, I don't know. So what is the analog of Daniel Gottsman's paper in the classical literature? Because they have to also do some decoding, and there, like, I mean, I know those things are not very relevant now because not that much amount of error correction is needed in computation at least. But I mean, there theoretically somebody may have looked at, and the question is, what is the best space-time overhead they got, in the classical literature?
Mhm.
So it's a bit frustrating. Like you try to bring the space down, but then time is running. Like, I mean, like, yeah. Mm. Yeah. Anyway, thanks. Yeah. Like, I mean, maybe somebody else's question.
Yeah, I have a question, like maybe not so relevant to the like theory part, but I mean for this like the fault tolerance scheme here, is it I mean nowadays is it experimentally implementable like with some practical
I,
platforms here like Looking's platform or
yeah, I don't think so. Like one implementation that I remember like from this Q era guys are
code atoms, right?
sorry?
Using code atoms, right?
Uh oh
I
yeah,
mean the platform.
yeah, I think so, yeah. Yeah, but they use like I think they just use like Steam code or something like that. But yeah.
Okay. Oh, you mean the Steam type
Probably.
aircraft, the fault tolerance scheme, like the Steam type?
No, like actually using
Uh,
Steam's code.
just the Steam code. Okay,
Yeah, yeah.
okay. I see.
There's like there's this paper on like HGP codes, but I'm not sure if it's an actual implementation. I need to double check on that. Yeah.
And like further question, like how do the experimentalists know we are fault tolerant to implement the codes or something? I mean, the like the fidelity or something.
Oh, like how you measure the performance, you mean, or?
Yes, I mean like you have a benchmark or something because I don't really know about this.
Um, I remember like Google has like this lambda factor that kind of like measure like how good do you scale. I'm not super familiar
Okay.
with that though.
You mean
Yeah.
the latest paper by Google, right?
I think they use it in all of them.
Okay.
Yeah.
I was wondering about this, the syndrome extraction, right? You basically have to prepare this GZ state every time. But actually, in practice, if you look at any kind of setup, they don't really care, right? You just don't do that, right? You just for every syndrome measurement, you just prepare like a single auxiliary qubit.
Oh, you mean yeah, but that's not fault tolerant.
Yeah, because
Yeah.
arrogant spread is there. But I mean, in practice, no one really bothers like to do this to prepare these GZ states because it involves preparing many auxiliary qubits, right?
Mm, yeah. Yeah, yeah, I don't know how practical like this Shore style QEC is, but yeah.
And the short this approach, because man, does this apply also to Toy code or service code,
Um
or you need like some other codes?
I I don't I don't think so because you need like each of this red block the K for each of this red block to grow kind of.
Or can you just put several service code together, like for the NI, right? You kind of scale up the number of service codes, like just put them next to the. I mean, I think just add two service code next to it, right? Then you have two qubits, then you add another two, then you have four logic qubits, and so forth.
Uh,
Is
yeah,
that allowed?
um I don't think so because yeah, you want some non-zero asymptotic rate. I think like that's yeah. Yeah. Right. Because yeah, because surface code or Tori code, like you have zero asymptotic rate.
No, but you could just increase the number of service codes, right?
Mm,
Like just put two service code next to it, or three or four or five, right?
yeah, I'm not entirely sure, but I think like there might be some things that, or probably like lots of things that you need to change in the threshold proof and stuff. Because like this non-zero asymptotic rate comes into the assumption, one of the assumptions. Yeah, I need to double check though. But yeah, for surface code, I think like this, there's this paper by Austin Fowler and others on like a fault tolerance scheme. It's probably similar. I'm not entirely sure.
Thank you.
Okay, so if there isn't any questions, we end here. I see you next week, maybe the last session, right? Okay.
Yeah.
You guys.
Right. Thanks, guys.
Yeah, thank you.
Thank you, sir. Thanks, Andrew.